at questions from H.C. Verma in hydrostatics and completed hydrostatics mostly with that. A couple of more types of questions in hydrostatics we'll look at today, and then we'll move on to hydrodynamics. So one of the things that is not there in HC Verma too much is about accelerated tanks. Okay, so let's and horizontal pressure gradient in accelerated tanks. So let's look at something related to that. So suppose we have this situation. We have a wooden block floating in water, which is stationary in an accelerated tank. So density of wood is, let's say, 0.6 gram per cc. And the tank is accelerated horizontally like I've shown over here. So a wooden block is floating in water in a tank accelerated at say 2 meters per second square. Take G as 10 meters per second square. So first of all, we want to find theta, the angle at which the surface of water is inclined at with respect to the horizontal. Then we want to understand the free body diagram of the wooden block and all the forces acting on it. Make the free body diagram of the wooden block in the frame of the tank. It's of course an accelerated frame. And show all forces acting on it. And from this calculation, next what we'll do is we'll calculate the fraction of its volume which is submerged. Okay, so use the values of density which are given in the diagram. Okay. Density of water is 1 gram per cc. Density of the wood is 0.6 gram per cc. The first part is of course formula based. Okay, so complete that and now do the second part. In second part, I'll explain in a moment, but what you have to understand is that horizontal pressure gradient is there. That means there is also a horizontal component of buoyancy. Yes, Dhruv, that is correct. Okay, people, my mistake. Today is session 5. Just make a correction there. Yeah, so as I was saying, that's correct. Theta's value through that you have mentioned is correct. Okay, now coming to the second part, okay, when you show the forces acting on the wooden block, okay, remember that it's in equilibrium in the non-inertial frame, but also in that frame, there is a horizontal pressure gradient. Okay, so there will be a horizontal component of buoyancy because of that. If you remember the derivation of Archimedes' principle for a floating object that we had seen, why there is upthrust? Because the pressure increases with depth. So like that, now the pressure also increases with the negative x-axis, because of the pseudo force acting on the liquid. So accordingly, there will also be a horizontal component of buoyant force. So that horizontal component of buoyant force has to be taken into account when we are calculating the, and that means, sorry, when we are basically understanding the free body diagram of the wooden block. I hope all of you got the answer for the first part at least. Okay. It should be tan inverse 0.2 or tan inverse 1 by 5. Now come to the second part. Tell me how many forces are acting on the block. Okay, so as I was saying, the first part is formula based, right? The vertical pressure gradient is minus rho g. The horizontal pressure gradient is minus rho a. So tan theta can also understand like this is the ratio of the vertical pressure gradient to the horizontal pressure gradient. So theta is tan inverse 0.2 or 1 by 5. You can leave the answer this way only. Don't need to find the value of theta. Okay, so now let's come to the free body diagram of the wooden object in the non-inertial frame of the tank. Okay, so first of all, mg and pseudo force. But now buoyancy will have a vertical component and a horizontal component. Be this, okay, and vertical component. So our net buoyant force actually will be like the vector sum of these two components. So our net buoyant force will be like this. The submerged volume. So density of water into submerged volume into square root of a square plus g square like this. Now in this non-inertial frame, this block is at rest. It's in equilibrium. Okay. So forces have to balance. So correspondingly, the horizontal component of buoyancy balances the pseudo force, okay, and the vertical component of buoyant force balances the gravitational force or the weight of the wooden block. Both equation 1 and equation 2 tell you the same thing, that the percentage of volume submerged or the fraction of volume submerged get the same result, that submerged volume is to total volume is equal to density of wood, density of water. This case is 0.6. So that is the fraction of volume submerged. Three-fifths of the volume is submerged, or 60% of the volume is submerged. So hope this concept is clear over here.
So can we copy this?
Yeah, just make sure you. So there is this important concept over here, this one, that due to horizontal component or horizontal pressure gradient, the water applies a horizontal component of buoyant force.
Sir, can you show the question for a second?
Okay. Okay. Now, for example, a simpler version of this question is like this: that if we had a tank of water like this, in this there is an object which is floating. Let's say a plastic body. So plastic body floats with 80% volume submerged in water. The water tank is at rest in the ground frame. Now next, if the water tank is vertically accelerated, also the plastic body of mass 2 kg, so is vertically accelerated. So next thing we are doing this. You still have the plastic block. So it is vertically accelerated at 2 meters per second square. Will the block still float? Make its FBD and show all forces. Acting on it in the non-inertial frame. And from that calculate the percentage of volume submerged. Okay, take G as 10 meters per second square. So this is actually a simpler version of that last question. Just try this out quickly and send me the answers.
Sir,
Yeah, tell me.
sir, for that FBD, sir, from which frame do we have to take, sir?
Non-inertial frame is mentioned, see.
Okay, sir.
Density of plastic is what?
See what's referred to in the question. And what is the first question saying? three forces are acting in the non-inertial frame. Okay, but the pressure gradient has become rho into G plus A naught, whereas horizontal pressure gradient is zero. So buoyant force will be equal to density of water into G plus A naught into volume of submerged part. So buoyant force should be equal to vector sum of mg plus ma naught. Okay. Now in the first case, when there was no acceleration, when you're looking at this in the stationary tank, so in that case, what was happening? Vertical pressure gradient was minus rho g. Okay. So we had original buoyant force B naught. So density of water into volume of submerged part into G was equal to mg. And in this, we saw that the volume of the submerged part is 0.8 times total volume. Now, when we look at this equation here, density of water into volume of submerged part into G plus A naught. On the other side has to be equal to M into G plus A naught. So when we compare equation 2 with equation 1, this and this, we see here that because this is what was given to us, that 80% of the volume was submerged. Whereas that is this, okay. So from the second equation, if you compare with respect to the first equation, you can see you're getting the same formula for volume submerged. So from equation 1, see that that is 80% of total volume. So yes, the block will still float. I have made the FBD and shown all the forces and what percentage of volume will be submerged, 80%. So while along with weight there is pseudo force acting, but also the pressure gradient increases. So the formula for buoyant force changes here because the vertical pressure gradient is no longer minus rho g. It is minus rho of g plus a naught.
Sir,
Yes.
sir, in the second equation, how did you get a row of water with V submerged parts G plus A naught, sir?
Because of this, because of the vertical pressure gradient. This equation here is giving us that indication.
Okay, sir.
So first equation is for acceleration, no? B equal to mg.
Sorry, first equation,
Before acceleration, no?
this above equation, this one.
Yes, sir.
No, this is in the stationary tank. This is the floating equation in the stationary tank. So buoyant force is equal to weight.
Yes, sir.
Understanding, no? So in the stationary tank, the vertical pressure gradient is minus rho g. So the formula of buoyant force is density of water into volume submerged into g. But in the accelerated tank, what happens? This pressure gradient changes to minus rho of g plus a naught. So according to the buoyant force's formula, the buoyant force is still vertical. There's no horizontal component because del p by del x is 0. Okay, as you can see here. But the formula for the vertical buoyant force changes. Is now density of water into V submerged into G plus A naught. Because in the gradient of pressure, G is replaced with G plus A naught. So remember, buoyant force acts because of pressure gradient. No?
Yes, sir.
Understanding the point? No? Because buoyant force acts because the pressure from below here, this pressure into area is greater than this atmospheric pressure. But now it is greater by what factor? Rho into G plus A naught into this depth. So accordingly, the formula of buoyant force will change. Same reason why in the last question we saw that when there is horizontal pressure gradient, there is horizontal component of buoyancy. So hope both these examples are clear. Okay, now next thing we'll move on to is the very last thing we will see. Yeah, Shikhar, so that's the reason because what is happening that in the case of this non-inertial frame, buoyant force also increases by that same factor as the effective weight of the object increases. You can think of this as like the effective weight. Okay, and this is also changing by the same factor. No? That's why the percentage of volume submerged does not change. See the formula of volume submerged we are getting the mass of the object divided by density of water. And it was the same in the first case also. Okay. So the value of buoyant force increases, but on the other side, okay, so you can see here that this density of water into V submerged into G plus A naught. This is a new value of buoyant force. If you compare it with the earlier value of buoyant force, it was density of water into V submerged into G. Now this was equal to how much? This was equal to the weight, which was given to us as 2 kg. You know? So mass was 2 kg. So this was 20 newtons. So now in comparison to that, the buoyant force has changed to this much times the earlier value of buoyant force. So it has changed to 24 newtons. But accordingly, this buoyant force is equal to mg plus ma naught. This is again 20 plus. So it is like you can think of this thing like the apparent weight. So the apparent weight increases to 24 newtons. Buoyant force also increases to 24 newtons, but it doesn't change the fraction of volume submerged because buoyant force's formula is also changed by the same relation, G plus A naught. Okay, understood now? So this is the important concept over here. Okay, now we'll move on to the last section of hydrostatics, okay, which is to do with pressure gradient, or what we call radial pressure gradient. In a rotating tank. So imagine now we have this kind of a situation. We have an open cylindrical tank. Which we are causing it to rotate, or it's made to rotate by an external agent. About its own symmetry axis. So what we'll see here is that if there is some liquid in it, then the surface of the liquid becomes this kind of a shape. Because there is a radial pressure gradient. So if we consider this to be a radial axis and this to be our vertical axis. So this is a cylindrical tank. So radius r, rotating at uniform omega naught about its symmetry axis. Now the cylindrical tank has water or any ideal fluid in it. So we have to find the radial pressure gradient. So why there is radial pressure gradient? Because of centrifugal force. Okay. Just like in an horizontally accelerated tank or even a vertically accelerated tank, there is a different pressure gradient. So in the case of horizontal, there's a horizontal pressure gradient because of pseudo force which acts along the negative x-axis. So like that over here, because of centrifugal force, which is the equivalent pseudo force in a rotating frame. So centrifugal force is pushing liquid radially outwards. So that's why the pressure now increases with radially outward direction. Okay. And that's why the surface of liquid takes this concave kind of shape, which we will show later to be a paraboloid. Okay. So the water will experience, the fluid basically will experience a radial pressure gradient. Of course, in addition to the vertical pressure gradient. Due to centrifugal force. In addition to the gravity that is acting along the negative y-axis, there is centrifugal force acting radially outwards. So that creates radial pressure gradient. Okay. Now to understand this radial pressure gradient, what we will do is we will consider a volume element of fluid over here. Which is of thickness dr. So we will consider that volume element of fluids free body diagram in the non-inertial frame, which is in this case the rotating frame. So in the rotating frame, there is at a distance r from the axis of rotation. So on this volume element, there will be centrifugal force, which will be equal to dm because its mass is very small. Okay, so we consider a volume element of area S, let's say, and thickness dr. So its mass like this. Okay. So this is the FBD with only the horizontal forces shown. So this is the centrifugal force on the element B. Okay. So centrifugal force, as you know, is a type of pseudo force. Now notice again here, P is equal to the pressure at R equal to R. P plus dP is the pressure at R equal to R plus dr. So the incremental pressure dP is del P by del R dr. Where this del P by del R term, this is the radial pressure gradient that we're talking about. So balancing the forces, because this one is at rest in this frame, in the rotating frame of the tank, that volume element of fluid is at rest. So P into S plus the centrifugal force balanced by the pressure into area from the other side. So the net horizontal force is 0. That's what we are showing here. Okay, so note down up to here. Then from that we'll be able to calculate the horizontal pressure gradient.
Sir,
So
can
can
you
you
do the
take
upper
the
part?
screen little bit up?
Sorry, come again.
Can you
सर
take
थोड़ा
the
ऊपर
screen
का
little bit
डेफिनेशन
up?
बताओ ना.
Yeah, which part you want me to explain?
No, sir, I want to just write the notes.
Ajay, the situation is clear now.
Oh, yes, yes, sir.
Okay, so see, balancing the horizontal forces, you see that centrifugal force acting on that element is equal to the increase in pressure along the radial direction into the cross-sectional area. So this is dm omega r. Remember, dm was equal to this quantity here. So we get this incremental pressure is equal to rho into omega square into r dr. Okay. Now this incremental pressure can be written as radial pressure gradient into dr.
Sir, it is a DPS, no?
Sorry.
Sir, the area is also multiplied, no? So division.
So S is cancelling now on both the sides. See,
Okay.
dp into S now.
Yes, yes.
So from this we can see that the radial pressure gradient is like this. It is so it's an instance of a non-uniform pressure. So it is directly proportional to R. It's not a constant. So there is a so the further away you are from the axis of rotation, okay, the more the rate of change of pressure, del P by del R. At the axis where R is tending to 0, the pressure gradient del P by del R is also tending to 0.
सर कैन यू सर वो डीपी वाला समझा सकते हो डीपी का वैल्यू कैसे आया del p by
Sorry,
del
come
r
again.
into dr. So the dp value.
Yeah, so that is coming from this. See, what is P? It is the value of pressure. P is the value of pressure at the point R equal to R. Whereas
Okay.
P plus dP is the pressure acting on the second surface. No? Now the second surface is at what radial distance? It is R plus dr. So the change in pressure is because of what? Because you're moving your distance from the axis, your radial distance from small r to small r plus dr. So that's why it's equal to pressure gradient in the radial direction to dr.
Okay.
Sir, sir, can you please explain the PS, sir, how the PS force is acting on P plus DPS force, sir?
How what is acting?
Can you explain, sir, in the free body diagram, sir, I was able to understand the centrifugal force, but I was not able to understand the PS and P plus DPS. Can you explain that?
See, on any body, there is pressure acting on each surface. I mean, there's force acting on each surface because of pressure. No? Now, this surface is of area how much? S. Okay, and the pressure in this region is how much? It's P, the liquid pressure. You understanding? So this surface will experience a normal force into it because of liquid pressure. So that will be equal to how much? Pressure into area. You understanding?
Yes, sir.
Now, similarly, at this surface, this is of area S, but what is the pressure here? It is P plus dP. So accordingly, what is the force because of pressure? It is P plus dP into surface area. Okay, so this is clear now. Okay, Jagannath, I'll go back to the first diagram. So now that we have understood that there's a radially outward pressure gradient, we understand why the surface is curved like this. Okay, now of course the vertical pressure gradient is the same. Yeah. So the vertical pressure gradient, when we want to consider, is the same thing. We don't really have to change anything. The same as the derivation we had done on the first day of hydrostatics. So the fact that it's a rotating tank doesn't make any difference to the vertical pressure gradient because centrifugal force acts horizontally. Okay. So now if we consider a volume element like this, which has a thickness dy. So I'm not going to repeat that whole derivation, but you can just understand that. So this is again in the rotating frame, but I'm considering only vertical forces on it. Because I've shown the equilibrium of the horizontal forces above. So you can see that it's the weight that has to be balanced with. And this time this dP is equal to del P by del Y into dy. So from this whole derivation, we get that vertical pressure gradient is minus rho. So radial along with vertical pressure gradient is present. Okay, so now based on this, when we look at the surface of the liquid, we'll understand how the shape is and why it is paraboloid. Okay. So now I'm just showing the cross section of the cylindrical tank. So according to us, the shape of the surface be curved like this. Okay. So how exactly we'll get the equation of the curve? So if we take this point as our origin, consider any point A over here, and below it B over here. This is our radial axis, this is our vertical axis. Okay. So the coordinates of the point B are 0, r. Y coordinate will be 0 because I've taken the origin here. The coordinates of the point A accordingly will be, sorry, not 0, r, rather r, 0. Whereas A is above it, so it is at y coordinate of y. Okay, so this distance is y. Okay, now pressure at O will be equal to pressure at A, which will be equal to atmospheric pressure. So that let's write as P naught. Is at origin, is at the point R comma Y. Okay. Now when we consider the pressure change from O, that is the origin, to the point B, which is at R comma 0. You have to consider that del P by del R is equal to rho omega square R. So the pressure difference integrated from the point O to the point B should be equal to this thing del P by del R integrated from R equal to 0 to R equal to R. Nothing but this thing integrated from 0 to R. So the pressure difference between the point B and the point O should be equal to this. Okay. So that's why the pressure at the point B, which is at a distance R from the axis, should exceed the pressure at the point O, which is atmospheric pressure, plus, so it should exceed by this factor, okay, omega square R square by 2 into density. So is the pressure at the point B expressed in terms of its radial distance from the axis. Okay. Now, similarly, when we also consider the relationship between the pressures at the point A and B, we will see we'll have to bring in vertical pressure gradient into account. And from that, we can also show that the pressure at the point B should be equal to pressure at the point A plus rho GH, where H is equal to Y. Okay. So here we have considered pressure change from O to B. Now, similarly, if you consider the pressure difference from A to B, you can see that you have to consider this. So pressure at B would be equal to pressure at A plus rho GY. Now pressure at A is equal to atmospheric pressure. And then we'll compare equations 1 and 2, and that is what will show us that this curve that I've drawn, which is the profile of the surface, it's a parabola. So when I consider that in 3 dimensions, okay, this I've taken the two-dimensional. When I consider in 3 dimensions, is this curve which is rotated about the y-axis. So it's a parabola rotated about its own symmetry axis. So that kind of a shape is called a paraboloid.
Okay, sir.
So the surface of liquid in a rotating tank like this takes precisely what we call a paraboloid shape. It looks like a concave surface when we see from above. But what is the exact shape of that concave surface? It is what we call a paraboloid, because it's a parabola rotated about its symmetry axis.
Sir, can you scroll up for 1 second?
Okay, so Durgesh, this is the point you wanted to repeat once. Which part, the radial gradient or the vertical gradient?
No, sir, I just to note down.
Okay, okay.
Done, sir.
Okay. Okay, so now when we compare equation 1 and 2, you can see how the radial coordinate and the vertical coordinate by point A. Okay, because equating the pressures PB for both of them, so you see P naught plus rho Gy is equal to P naught plus rho omega square R square by 2. So from this you can see that P naught cancels out, and you can just write Y is equal to omega square by 2G into R square, or Y is equal to some constant into R square. Okay, so this is the equation of the surface. That is the Y versus R for the surface. Now remember, the actual surface is three-dimensional, so R is a rotated axis. So when you rotate this about the y-axis, the shape that you get is a paraboloid. In 2 dimensions, it's a parabola. That means it's a paraboloid surface. So from the vertex, which is the origin, okay, which we had seen here, if we look at any point on the surface, the vertical elevation y is related to the radial distance r by this kind of relation. Y is equal to some constant into r square. So that kind of a surface is called a paraboloid surface. Okay, so with this we complete hydrostatics part. Okay. So we'll take basic look at hydrodynamics basics or fundamentals today, and next lecture we will look at more precisely the derivations and things. So we come to the second part of fluid mechanics, which is hydrodynamics. So in this we are still dealing with ideal fluids, that is non-viscous and incompressible fluids, but now we are discussing about them in motion, so hence the term dynamics. However, we are going to discuss a very specific type of motion of ideal fluids, and that is we are going to talk about something called steady flow. Okay. So steady flow, or another name for it is streamlined motion. Of ideal fluids. Okay. That is what this chapter is all about. Okay. So ideal fluids, you of course remember what they are. Okay. Ideal fluids are incompressible and non-viscous fluids. Now let us understand what is steady flow. Steady flow is the type of flow for an ideal fluid such that the motion of the fluid volume elements is non-turbulent and irrotational. So I'll explain each of these terms, non-turbulent and irrotational, in a moment. Just make a note of this definition first of steady flow.
Done, sir.
Okay. So what does non-turbulent motion mean? So turbulence in fluid flow. Here, of course, it is non-turbulent. Okay. So turbulence in fluid motion occurs when there are sudden changes in pressure, okay, due to can say due to extreme magnitudes of force from collisions of volume of fluid volume elements with rigid surfaces. So it typically occurs in high velocity flow with random collisions with solid surfaces. So example of that is a rapid waterfall. Okay. So in a rapid waterfall, if you visualize the fluid elements or the volume elements of fluid as they are moving, they undergo frequent and random collisions with rocks and with solid surfaces, uh, or even with each other. And because of those high velocity collisions, okay, there is large magnitude collisional forces which are acting on the volume elements or on the surfaces of volume elements, creating extreme changes in pressure, sudden and extreme changes in pressure. In fact, it is sudden and extreme changes in pressure. Okay. So this creates the phenomena of what we call turbulence. Or another example is smoke coming out at high pressure and density from a narrow chimney. So in this type of example also, you can imagine that the volume elements of fluid, of course, smoke is a highly non-ideal fluid because it is highly compressible. But here we are talking about turbulence. Okay, so turbulence occurs in this kind of motion also. So typically for turbulence, we need two phenomena to be there. One, that the motion of the fluid, it doesn't matter whether we are talking about ideal fluid or non-ideal fluid. We're talking about turbulence here. So in turbulent motion of any fluid, there should be high velocity of fluid flow. And secondly, during that high velocity flow, there should be random and high velocity
Collision.
random high velocity collisions that occur with rigid surfaces, and the collision impulses are what create these sudden and extreme changes in pressure. That is what creates turbulence. Non-turbulent motion, these things should not be there. So there shouldn't be any extreme and sudden changes in pressure due to any such collision phenomena. So therefore, in steady flow, which is by definition also non-turbulent, there are no sudden and extreme changes in pressure. At any point inside the fluid. Okay, now if we talk about irrotational motion, that is, as the name suggests, that is, there is no rotation occurring for any volume element as it is moving. It is in pure translational motion. It implies that volume elements in motion are purely translating and not undergoing any rotation. Okay, so when we put together these two properties, the non-turbulence and the irrotational nature of the motion, we also see a very important property of steady flow, which suggests why it is also alternately called as streamline motion. So this is a visual representation of steady flow of an ideal fluid inside a pipe, in this case of non-uniform cross section. So now if we consider any volume element of fluid as it is moving, at a time t, this volume element of volume dV or mass equal to rho into dV, if it has a velocity v like this over here, okay. Now after a bit of time it might reach somewhere here and its volume would have become v plus delta v. Now the very important thing here is that when a volume element moves on from its current position to its next location, some other volume element is coming and occupying the first one's position. Now that second one that comes and occupies the first one's position should have the exact same velocity vector. That is the important property of steady flow. And that happens because there is no sudden change in path because of collisions. And also undergoing rotation. As you can see, they're undergoing pure translation, the volume elements. So these two properties of the non-turbulence and the irrotational nature of the motion, or the translational nature of the motion, they take care of this important property of steady flow, that if the instantaneous velocity of a certain volume element, which you can basically treat like a particle of fluid, okay. So if a certain volume element is v at t equal to t, okay, then at a different time, at a different instant of time, t plus delta t, a different volume element that now, or you can say that is now located at the same position, will have the same velocity. Okay, so this implies that volume elements in a steady flow move along fixed paths or trajectories, okay, such that they kind of follow each other precisely, and each point in a trajectory has a defined value of velocity. Okay. So these trajectories of fixed paths along which the fluid elements move, they are called the streamlines, and hence the motion is called streamline motion. So these fixed paths or trajectories okay, and hence the motion is called streamline motion or streamlined flow.
Sir, can you take it a little bit up?
Yeah. Okay, done.
सर इसमें नोट में सर जो आपने देन डिफरेंट इंस्टेंट t इक्वल टू t प्लस डेल्टा t वो वाला पॉइंट नहीं समझा सर.
Sorry, at a different instant t equal to delta t. Okay, so what is happening? See, at this particular instant, there is a volume element that is present over here, which has a certain velocity v. Okay, this is at t equal to t. Now, after some time, this volume element has moved somewhere ahead. Okay, और यहाँ पीछे कोई और वॉल्यूम एलिमेंट था, वो आके ये वाले पोजीशन को ऑक्यूपाई किया. Understanding the point?
हाँ सर.
So now the new volume element that is present over here now at t plus delta t, it will have the same velocity as the earlier one had. So it's like each volume element is following the one in front, and its velocity profile is changing according to how this one is changing. The best way to visualize this is now, imagine traffic moving in a very ordered manner in proper lanes, and nothing is changing lane. And also the distance between the vehicles is not changing. Okay, so that is an example of like traffic moving in streamlined motion, as opposed to unruly traffic where people are changing lanes, or maybe collisions are occurring, because of which some of the cars are also undergoing, that random turbulence. So they will undergo random rotational motion when a collision happens. So that's an example of extreme turbulent motion in a traffic. Understood now?
हाँ सर.
Sir, can you take it a little bit up for till irrotational?
Yeah.
Sir, can you show the last part?
Yeah. Okay. So basically, what we do to construct the streamlines is that at a given instant of time, if we randomly select some different points in the fluid and we draw the velocity vector of whatever fluid particle is present at each of these points. So like that, we draw a lot of velocity vectors, but we draw them as very small vectors, like differential arrows. Now, if we join these arrows into smooth curves, then they will represent the streamlines.
Streamline.
So streamlines, these are, you can say, they are a visual representation of the steady flow of an ideal fluid, such that at any point in a streamline, the direction of the tangent is the direction of the velocity vector. Okay. So in the streamline that we are drawing at a particular point, going through a particular point, if the streamline has a tangent particular direction. So at this point, if I draw the tangent, let's say the tangent is in this direction. So the velocity vector will be along that direction. And the other important property of the streamline is that if streamlines come closer together in a certain region, then the magnitude of velocity is greater in that region. Whereas if they are wider apart in a certain region, the velocity is less. So the streamlines are packed closer in regions of higher magnitude of velocity. And packed more loosely in regions of lower velocity. Okay, so naturally you can see that in regions where the cross-sectional area of the pipe itself is becoming smaller, the streamlines are packed together more closely. And where the pipe is wider, the streamlines are packed together more loosely. So if we have a pipeline in which the area of cross-section of the pipe itself is changing like this from A1 to A2. So you'll see that the way the streamlines are packed together, they'll be wider apart where the area is more, like A2. And they're more close together at A1. So the velocity of flow in this region will become more than the velocity of flow in this region. In fact, later we will see that there's something called continuity equation where A1 into V1 is equal to A2 into V2. So Pratyush, to answer your question, okay, if we have a pipe of uniform cross section, it is actually more likely to undergo steady flow in that, okay, as long as we don't pressurize the liquid too much for it to go at high velocity, where its motion becomes a little bit more random. In fact, what will happen is in a pipe of uniform cross section, the velocity of flow will have a uniform magnitude. Understood my point? We
Yes, sir.
can create, yeah, but to answer your question, that can there be turbulence in a pipe of uniform cross section? There can be turbulence, okay, particularly if the pipe is curved and we try to pass liquid at high velocity through that curved point. Okay, so we might have a pipe of uniform cross section, but for example, if the pipe has a sharp turn over here, okay, and we try to pass the velocity, the liquid at high velocity, so it is not able to maintain that streamline kind of path. Then as it comes at the corner, it might undergo turbulence. But even in this case, with a sharp corner, reasonably sharp corner, that is, okay, nothing will be a perfectly sharp corner, because when you look at it at a magnified level, it's always a little bit curved. So even in a reasonably sharp corner, if the flow velocity is comparatively less, then there will be some degree of turbulence, but it can be ignored. More or less, we can say that most part of the liquid is moving in steady flow. Whereas if the flow velocity is high, then definitely near the sharp corner, a significant region of the liquid will experience turbulence. So hope that clears your point, Pratyush.
Yes, sir.
So it is possible to create turbulence even in a pipe of uniform cross section, but that should have some sharp turn at some particular point, and we should be trying to make the liquid pass through that turn at a high velocity due to high pressure. So that situation can create turbulence even in a uniform cross sectional pipe. Okay, so people, we will conclude here today, and next time we will see the mathematical equations used to describe this kind of steady flow, which are namely called the continuity equation, that is A1 V1 is equal to A2 V2, and the Bernoulli's equation that relates the square of the speed, that is V square, with the pressure, which is pressure at a point, and with height of the point with respect to some horizontal ground level. So it relates basically something like potential energy, gravitational potential energy per unit volume with kinetic energy per unit volume with pressure. Okay, so the relationship between pressure, the flow velocity, and the gravitational potential energy per unit volume at a point. That particular equation is called Bernoulli's equation, and that is the standard equation that is used for solving anything to do with the numerical relationships involved in streamline or steady motion. So we'll look at that in the next lecture and some of its applications. Okay. So that's it for today's session, people. Wish you all the best. And thanks for attending.
Thank you, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye.
Okay, people. Bye.